Welcome back to the second part of this fifth module and webinar of Euclid. We are now focusing on actual frameworks that are very practically supporting the building process of linked data applications with some examples. And after that, take a deeper look at some aspects that we had spared out from the general architecture so far. Well, first, there's one framework called the Information Workbench. The Information Workbench is a linked data application development platform, which roughly corresponds to this three-tier model. You have a data tier where data is being imported, it's then managed. There is some sort of logic tier with components such as workflows and similar things, and there's a presentation tier where the interface is being visualized. Talking more about the component aspects and about how this framework supports the building process of your own linked data applications. You have your resources, all your data from different places, which might, to a part, be linked data already or otherwise exist in totally different formats, like data from industry systems coming from social APIs and so on. Then the platform can take those on. There is a complete set of components to import those data, load them. And then there is also a workflow engine and components in the platform to support various processes, workflows, and tasks, such as search and analytics, and a semantic wiki engine. On top of that, you have a rich SDK that you can use to build your own applications. There's an API if you really want to extend the platform, interact with your own programmed components. And there are several ways to configure the basic platform to make it work precisely the way that you need for your applications. Then there are rules. There are so-called data providers, which are the tools to get in your data from the various sources. You can have an ontology, which of course could stem from the different data that you're loading, but typically it would be separate. Either you import it once, for example, a predefined ontology or something that you have curated manually in a tool like Protégé, or if it's a simple vocabulary, you might also author it within the platform. Then you have access to your data, a templating system to style your interface. There are workflows supported, and you have widgets to use in that interface. On that basis, you can build any kind of application. For example, the MusicBrainz Explorer, which would correspond to an example of our motivating scenario. There are others, such as data center management. In fact, the EUCLID Manager application that we have talked about earlier is one of those applications. And there are many more. To access the data, we are basically using an open source framework called Sesame OpenRDF, which is a very popular RDF and RDF management API and system. That's the basis that we're plugging in here. This also comes in a layered architecture. There are triple stores at the very low level, which can be replaced by other components. Then there are so-called sail layers, which are basically access layers to the linked data, to the RDF data. And then on top of that, we are interacting with this open framework to get to the data and store our data. There are several ways on how to configure this data backend. A local, the most simple way, would be to access a Sesame native store, which is the built-in very simple hard disk based storage of Sesame OpenRDF. The same thing can happen locally with different databases, different triple stores on the lowest level, not the Sesame native store, but for example Olim or others. Then another possibility to set this whole thing up is in a more clearly separated way, separating the tiers in an architectural, clearer fashion by using so-called remote repositories. Now, a repository, basically, whether local or remote, basically is the component that provides the database. A remote repository would be a database running in a separate process on the same machine or some other server, while a local repository is a database process started within the information workbench process, just running as a separate thread, for example. In the remote repository, we have a separate database running, which can be used by the information workbench and possibly also other applications on the same server or some other server. Then again, you have any of those options of using the native store or some other triple store, and can still access all of that. And then there's a third option, though this is less often used, where you don't use a triple store at all, but directly run the information workbench against some Sparkle endpoint, which can provide all of the data. To integrate data, there is a set of data providers. Data providers come in a certain assortment with the platform. You can also write your own providers. And data providers access data in some way from somewhere, load them into the database, cache them, store them into the database. So the information workbench is basically implementing the crawler pattern in a manner of speaking, caching or locally storing all of the information. Data providers run either once or, more typically, in a periodical way. So you configure how often the data should be updated from the original sources. There are different providers to access different kind of data. For example, you can have a Sparkle provider which queries some remote Sparkle endpoint with a construct query to get all of their data or some of their data. You can have an RDF provider accessing RDF dumps or some other RDF interfaces to directly download a series of triples. Then there's a host of other providers, such as XML to RDF conversion, such as virtualized R2 RML access, which means to access relational databases through a relational to semantic mapping, or also one of the most general purpose providers, a Groovy script provider, where you simply write some script using the libraries and APIs in the backend to transform any data that you can read out somewhere on the web with your script and push it into the database through the provider mechanism. What this is doing is implementing a crawling pattern, or more generally speaking, storing the data in a warehousing approach. Data warehousing is what you also have on a non-semantic level, when you simply take on data from different sources, typically within one company in the classical case, and integrate them into one big database to run analytical queries over the combined data set. To that end, data is typically copied over, rearranged in a way so that a huge mass of data can be queried on, and therefore it's only periodically being loaded. With the crawling pattern that we have here for the information workbench, that's nothing different, just for linked data from different sources that we integrate, that we transform, that we rearrange in such a way that they can be used with one application asking queries against all of the data set. But there's an alternative to that other than this warehousing pattern with the data providers that update the data periodically. You can also run a federation. Well, as we said before, a federation of different SPARQL endpoints can be used to send one query distributed over all of those SPARQL endpoints, get results from each of those individually, and then put them together. This may mean that my federating layer, the coordinating component in the federation, already knows that some of those sources can answer certain queries and others cannot, so it can send them the queries instead of to the others. This may mean that it knows that some part of the query can be answered here, some other part over there, and then ideally it would split up the query. And it could also mean that the layer knows, okay, each of those could, at least potentially, ask some part, and I don't really know which, in which case the query would have to be replicated everywhere. You see how complicated that can get. In the information workbench, a system called FedEx can be used to provide a fully visualized, fully transparent federation where you can configure a number of SPARQL endpoints, and FedEx coordinates those, analyzes the queries, and performs a certain degree of optimization as far as possible here to not overload individual endpoints and not to push more traffic through the network than necessary. Having the data in the system, there's of course all the logic in between, and then there's first and foremost an interface. So for the music application, we have something presenting artists and other aspects around music. There's a customizable interface with several basic components that can be configured to be there, to not be there, to look different. In the middle there's the big view where we have this information about music artists mostly on the screenshot. Then on the left-hand side there's a tabbed menu to choose between different views of that. As you see a title on top here, some basic functionality in the upper right corner. Right here, the view is a wiki view. And as a wiki can typically be viewed, edited, and can have several revisions, you also have those small tabs also to the right, relatively on the top, to switch between those different views on the wiki. The concept behind that whole thing is to have one view, one page for each resource. We have URIs, those are in the data. Each URI, each resource is associated with its own distinct page. For example, one for the Beatles, one for Rihanna, and so on. Then there can be that ontology. And this makes it possible to run the platform in a data-driven way. Each of the instances, Beatles and Rihanna again, have their own pages. But they also have their types, which is something associated through the ontology. And their types can have templates, as you can see on the upper right side here. So you would write one template for the class of music artists that structurally describes on how all the wiki pages of each of the music artists would look like structurally, unless you override them. And you do the same for all of the other kinds of classes that are relevant to you. And then all of the individual pages, as soon as data exists in the database, as soon as we know that the resource Beatles is associated with a music artist, that template is being drawn and the page can be rendered. There are different views, however, not only the wiki, which often is the typical end-user view. But you can also have a table view, which is rendering all of the information associated with that resource in a structured way. So you see all of the properties, all of the predicates, and all of their values in an expandable, flexible view to browse and possibly navigate to other related aspects that might not or not explicitly be visible on the wiki, because that's more end-user tailored. Then you can have something as a graph view, rendering the structural neighborhood, the semantic neighborhood of the resource that you're currently viewing in a graphical way. Or things like a pivot view, which allows to statistically display some of the related content, how many of which are there. In general, the interface is widget-based, and widgets are also provided by the platform in a rich assortment and can be extended through the API. You can add your own widgets with your application, but there are things like, for example, a map widget that allows to display locations. If there are locations associated with your content, say a music artist might have a place of origin, which you may want to display like this. Then there can be analytics and reporting. That's something you would typically display on an overview page, such as a class, where you might report on all of the individuals on that type, for example. You can integrate external content through mashups, for example, from social media, associated Twitter streams, or things like that. And there are widgets to create content, to produce new link data, or manipulate it. All of the widgets can be controlled through configuration within the wiki, which is semantic media wiki syntax with Sparkle queries in there. You simply have parameters to the widgets. The most important parameter typically is a Sparkle query. Sparkle, as we know, is a standard way to access linked data. And with that query, all the results are being flexibly retrieved from the data that are needed to render a certain component. In this case, we're rendering a bar chart on releases. Talking about the music artists, we can have a page of a class that displays a list of all the individuals. This is one fixed query. Here rendered with a widget that gives us a table, tabular view of all the individuals. That's something you can add it in the wiki, you add that widget and the description and so on. Instances, for example, then are driven by a template, not by a concrete configuration in the wiki, like that overview page, which only existed once. And for this, we can have something like the Beatles, and there was a template, and according to the template, we're rendering here a picture of the Beatles, which was in the data, a short abstract about the band, some related links to instances of all the musicians who have played at some point in time as part of the Beatles, and also a location where the band was based, and as a mashup component from the web, a set of tweets around the official channel of the Beatles, which is still managed by, I guess, the record company. And to add external content, well, that's simple enough as well. You have a particular widget, say a YouTube widget, by which you simply say, okay, here it's not a Sparkle query at first, but I want to send something to YouTube, which gives me the right videos, which would be a keyword search. And to say which keywords should be searched for, you can, again, use a Sparkle query. to query relevant associated aspects, say the name of the current resource, and then the name of the current resource, which of course would be the Beatles, would be sent to YouTube, and in return you get whatever video they first present you. To additionally also modify, change, add content, there are different other widgets available. There's the triple editor, for example. This is implemented on top of that structural table view, where you can structurally view all the related triples of a resource. There, if you have the permissions, you can also edit the data, add new triples to that resource, or edit the values of existing ones. This is guided by the ontology. So if you do have an appropriate vocabulary, you will get suggestions which new properties you could add, because the ontology says there may be relations here. There may be appropriate, it may be appropriate to add such triples. Also based on either the ontology or a more manually placed configuration, data can be validated. What kind of input is eligible for a certain property? You can have data type restrictions, and if you enter something different, you won't be able to add new values that would hurt this constraint. There is more information available on the information workbench online, and especially also on a demo system about our motivating scenario of that music linked data platform, which is available at musicbrains.fludops.net. Also, you can download a community edition, a free version, available in open source of the information workbench, if you wish to try it out. But of course, that's not the only framework there is in the sphere of linked data. There are others that are partially addressing other needs. For example, there is Callimachus. Callimachus is a very visual, very web-oriented tool to build linked data applications. There is a web front end that you can use to create resources, to create associated configurations, and thereby build your linked data application. There is the Linked Media Framework, abbreviated as LMF, from the Apache Foundation, consisting of several components that partially have very intriguing capabilities. For example, there's Apache Marmotta, which is a linked data platform on its own. Marmotta provides a series of capabilities, both for consuming linked data, republishing linked data. It comes with its own little triple store, and with various capabilities to build linked data applications on top of it. Then there's Apache Stanball, which is different from the previously presented frameworks insofar as Stanball is about one very specific aspect that you can often stumble upon when you build linked data applications. It's about extracting content. It's about making sense of non-linked data, of plain text, for example. And finally, there's Apache Solr, which concerns itself with indexing. Check it out. Another very intriguing and unusual approach to linked data application development frameworks is Synth. Synth is special on a technical level, from top to bottom. For once, it's built on Ruby on Rails. But that's not the big thing here. The big thing is that Synth uses a principle which is called semantic hypermedia design method. And in the semantic hypermedia design method, there is a semantical meta model which describes how the application should be built. And then you hand that model to Synth, and it's running the application based on that model. Linked data application frameworks will usually help you to build your applications in much less time than you would take to build it from scratch yourself. And within those, you can use a good knowledge of the architectural patterns that we had discussed before, but there's one big topic open that we haven't talked about so far, and that's especially if your linked data applications is operating on the web. You might need to use web APIs or provide web APIs. And all the web APIs rely fundamentally on internet technology, web technology, in particular on HTTP, the Hypertext Transport Protocol. Simply put, it's a client-server request-response protocol where a client sends a request to a server which reacts with a response. There are different types of requests in HTTP. The most popular ones that you have maybe heard of would be GET and POST. You send a GET request to retrieve the content behind a certain resource, a web page, for example. You send a POST, third on the list, to submit certain data. On the regular web, that's typically form data. You enter your credentials into a form and post it to the server to send it there. There are other methods that are also important, in particular if we are not thinking about mere web browsers, but about other ways, API ways, to use HTTP. There's PUT, for example. PUT uploads data to the server. It should put them on the server for the server to keep it there. Then there's delete, or the way around. There are more such operations like head, which is a what would be if kind of request. So you're sending a request to just retrieve some header information of what you would get if you were really asking. More others exist like that. So, and besides, for the method, you send the server a URI, a resource identifier, to say where you want to do that, what you want to get, or where you want to put to, and so on. And a header, which gives a little more specification on what you want to do there. And then optionally, some body part may follow. For example, if you post something, it's not enough to say, I'm posting to this URI. Of course, you also need to add what exactly it is you want to post there. In response, you'll first get a code, which is an identifier telling you how well it worked, basically. There are a few you'll know from web browsers. The 4 and 5-ish probably. There's the 404, page not found. There's the 500, internal server error. You've seen those probably. 1 to 3 are less often seen on the web. That's because those codes starting with 1 are provisional. They're just intermediate messages from the server to the client. Hey, stick with me. I'm going to send something soon. That kind of stuff. The 2-something messages are just confirming that something worked successfully. So basically, whenever you're navigating your web browser to any web page and it's loading, that implies usually a 200. Okay. Here's the stuff, but you're not seeing the 200, but instead the web page, of course. And now it's getting interesting. There are the 3 codes, 3 something, 300 something. And those indicate that this might work, but not like this. Further action is needed. We'll talk about that in more detail just after. So the 400, I gave you that example, page not found, for example. That means that you have sent a request that the server cannot and will never answer, not like that, because it's simply wrong in terms of what the server is offering. While the 500 codes indicate that the server messed up, that something didn't work there. It should have worked, but it didn't. Okay, so let's play with that. HTTP request, a client submits it, let's say to Wikipedia, and the client says HTTP GET, it should add a version there, HTTP, I'm speaking HTTP and the following version, dialect, and now get me the following URI. And the server answers, well, okay, that works, 200, here's the page. Can be more tricky than that. Let's say we're not asking Wikipedia, but DBpedia, the page that tries to store structured knowledge about all the stuff that exists on Wikipedia as well, but there it's manually crafted text. Again, we're saying get, give me the Beatles, and I'm a web browser. I want to see some HTML. So I'm adding a header, which says I'm accepting content type text HTML, which is a MIME type. And other than Wikipedia, which would have said, yeah, I know what you want. You don't even need to tell me it's text HTML and don't have any other. I'll send you that. DBpedia says 303, see other. Now I don't have that here. I kind of know what you mean because I have that resource identifier for the Beatles, which is my unique identifier for the Beatles. And I understand that you want some HTML that is describing this resource, the Beatles. But at the place of the resource, there's not the HTML. That's simply the identifier. That's the idea of the Beatles, so to say. And I'm clearly differentiating that. So instead of saying dbpedia.org/resource/the Beatles, you have to look over here at dbpedia.org/page/the Beatles, which is where I'm storing the web page, the HTML document that is describing my unique resource of the Beatles. And this procedure with the client saying, I want to have some HTML about that resource. And then the web server is saying, okay, I have that, but not here, but at a different URI. Look over here. That is called content negotiation, or CONNEC for short. The client says what content it wants. The server says where to find it. And this, of course, only makes sense if there are different types of content that can be found associated with that resource. So now it's a different client. It's not a web browser. It's some linked data application. Your application, for example, that wants to get text describing the Beatles. Apparently not as HTML, but as linked data. Let's say as text turtle, which is the turtle RDF format. Then we get basically the same request. It's a get to the resource of the Beatles, and it says I'm not accepting HTML. What I'm accepting is text turtle. And then again, the server says 303, see other. It's not here. I have it there. And here you look at dbpedia.org/data/beatles.n3, which is where I'm storing the RDF describing the Beatles. And this is a pattern that can be very well used to publish linked data through a web app, having resources, identifying all the information, and then redirecting depending on the type of content that is requested to either a web page or some RDF content or something else even. So, and now our crawler goes on there. Okay, I have to look at dbpedia.org/data/beatles.n3. I'm still accepting turtle only. And then the web server says, yep, fine, that's it. 200, okay. Here's the RDF data I have in turtle. Well, web APIs. That was the foundation. That's how you could simply make RDF accessible. But how does this make an API? It does to a certain part already. But the general motivation for APIs is that the web has not only static data to offer. If there are only things like the Beatles, resources whose description might change occasionally, but not too much, and it's still always the same resource. But there's also dynamic data. There is a lot of data that is being created spontaneously as a reaction, for example, of a user request. There is very state-depending data, such as weather information that quickly changes. Moving objects are a classical example of things whose properties are changing very frequently. And web APIs can be used to address those needs. You can have things like web APIs or services, web services, with service endpoints, which are URIs basically, that answer such requests. And by doing so, you're basically programming. You're basically sending requests that are answered in a direct reaction of your very specific request. There's a large number of web APIs accessible in general. They are not primarily linked data web APIs, but web APIs. And the most important, most popular type of web APIs that can be found out there are REST APIs, which stands for representational, I'm sorry, I tried to be a little less tongue-twisted, representational state transfer. Basically, REST APIs are an architectural style for client-server interaction, and it's focused on the web architecture. Web APIs thereby implement the programmable web, and the number of existing APIs has grown massively over the last couple of years, from almost none in 2005-06 to several thousands. And the REST plays by large the most important part, with around 70% of the APIs available acting on the basis of the REST model. There is one criterion to describe the quality of REST APIs. There are several others. This is one, which is called the Richardson Maturity Model for REST services. And it has 3 levels. Resources in URIs, then HTTP verbs, HTTP terms, basically, keywords. You could say it's called HTTP verbs. And then a 3rd level, which goes by an unspeakable acronym and is called the hypermedia constraint. On the 1st level, URIs, you're just saying we talk about resources. Our web API offers URIs that associate resources. We don't talk about endpoints that can encode any number of different, semantically different aspects that can provide any number of answers to any number of unrelated things, but we're talking about resources that are clearly identifying things. So for example, you would have a resource to access the Beatles for your request through Web API. Then on the 2nd level, you don't only have resources, but you address them using HTTP verbs, which are those types of requests, from get over post to put, delete. Options would be another example, where options simply gives you the list of other verbs that can be appropriately applied here. And then on the other side, the server would respond with the HTTP response codes. So what does this give us? First of all, some standardization, something I can expect as a client, and something I can reasonably implement as a server. But it's also giving us some additional semantics on those verbs, because they are defined with HTTP. There is a safeness characteristic. Safeness guarantees that the operation will never change the resource addressed on the server. Get is such an example. A get operation should retrieve something. It should never modify the resource addressed. Then there's a property called idempotency. So this is not exactly according to the more general definition of idempotency. A verb is defined to be idempotent in HTTP if it has no side effects on the resource. For example, if you delete a resource and you send a delete a 2nd time, the resource should still not be there anymore, no matter how many deletes you send in a row. However, the response sent by the server is different. The first time when it works out, you get a different response than the next time when it wasn't there in the first place. So response may change, and we still call it idempotent, but the side effects must be the same. And well, there are several verbs like delete that should guarantee that. And by knowing all of those guarantees, you can know what to expect when you send a certain type of request to a web API at some resource. Then at the 3rd level, the hypermedia constraint, which has that acronym which is spelled out as hypermedia as the engine of application state. That's a principle where we say we'll use different resources to still, the resources have static URIs in a way, to still move an application through a series of different dynamic states. This corresponds in a certain way to things like an automaton. So, for example, a client can send an order of a music album to a web API. Web API is here at HTTP and so on, service.org, some service, /music/order. That's apparently where orders should go. Then the client sends an order which says, here, this is an album, and this has some universal ID associated with that, a code, and I want to order that. Then the API would say, okay, I'm creating you that order, which is a new resource. So it says I've created that resource, and it's this order number 001, which is a order, and it's about this album that you want to have. I'm also telling you the price, and not only I'm telling you the price, but I'm also saying, okay, this is in a transitional state of awaiting payment. This order isn't completed yet. I want ship, and even less, you have already received it. But here, I'm also telling you where you could pay at this other resource that I also have created for the purpose. Simply go to 001 subscore pay to submit your payment details. And then the client can do that, submits some more details to that other new resource, credit card number, for example, and then we'll get another response of the order being updated to a state of in shipment, or can be downloaded, maybe with an address where it can be downloaded. And except for such APIs that can be built to especially work with linked data, there are a series of other APIs available. Many other APIs available that we still may want to use. Freebase is a popular service now owned by Google, where semantic data is being collected on a wide variety of topics. Freebase offers a set of APIs, and Freebase, thankfully, by now also offers an API to retrieve RDF. So you have that URI for the API, which is something at Google APIs, Freebase, and so on, the version. You say you want to have RDF, and then you add the ID from Freebase, the object that you want to get RDF about. So, for example, you can send it something to address things about the Beatles, with have an ID of M/07COJ something. And then Freebase, which is representing its semantic data in a non-RDF fashion internally, will map all the so-called facts to RDF triples and create those. They have to work a little on that because they might contain aspects that are unusable in abbreviated URI stuff, so they're replacing a few identifier characters, and then you'll get back some RDF with typically the first 100 values for each of the predicates associated there. So you get something like, yeah, here this is my namespace and total, and then here it's all about that Beatles ID, and there are some awards I could tell you about, and there are websites associated with them, and so on and so forth. More services are offering APIs such as Freebase, but even more offer others that are not actually available as RDF, as linked data, but are implementing JSON-like or other APIs that you can still wrap to import the data, to turn it into RDF and use it. Very popular ones would be Twitter, for example, where you can access timeline, tweets, all kind of tweets. There is even streams, direct messages, and so on. There's Last.fm as another example. All kind of information around music. This is very relevant with relation to our motivation scenario again. And there's Foursquare and many others. To wrap up, linked data applications have certain characteristics. Linked data applications should consume linked data, otherwise there are usually no linked data applications. They also should manipulate and or produce linked data. If they don't, we normally don't consider them as full-fledged linked data applications, but rather as mashups. And then there should be an application, an interface, typically a web app. Also, we can categorize them, classify them according to 4 important dimensions. There's the semantic technology depth. Applications can be intrinsic or extrinsic. There's information flow direction for extrinsic applications only, which says whether they're consuming and or producing data. There's semantic richness, strong, shallow, and semantic integration, how much vocabulary is being reused from other sources. But the architecture of linked data in general, typically you have a multi-tier architecture, which often kind of resembles the 3-tier architecture from web apps in general. And also quite often you would use a wrapper mediator pattern to include heterogeneous, non-uniform data sources from elsewhere. To consume linked data, there are 3 basic patterns: crawling, which reads in data, caches it; on-the-fly dereferencing, which immediately reads all data on request from remote sources when they're requested, does not cache them, and then a federation, where you have federated sources, typically with sparkle endpoints, that you can query against. The main components of that architecture in the various layers are a triple store, whenever you're not doing on-the-fly dereferencing, logic components, which can be integrated with a triple store partially, UI components, of course, to implement the presentation layer,